Okay, in this video we will look at differentiating some basic exponential and logarithm functions. I actually started with the logarithms, and I wanted to do this because everything we're doing um, in this section that has these type of problems actually relies on some previous uh, knowledge, some algebra with logarithms. So let's get going. We could have done a whole section or even week of review, and I'm not saying it would be bad, but we just don't have the time um, to take this course. You should have passed the college algebra course already, so therefore you're responsible for remembering these, and a quick refresher, there's nothing wrong with that. So two things. First off, the derivatives of e to the x, an exponential, and the derivatives of a natural log, ln x, are probably the two easiest derivatives you're going to see. The derivative of e to the x is simply e to the x. The derivative of natural log of x is 1 over x. I'm going to refer to those here shortly. So in future sections, and it really depends on the textbook, the order that you see the material, but in future sections we'll see things such as a product rule, quotient rule, and a chain rule, and I'm doing this video based on the premise we haven't learned any of that yet. So if I know the derivative of natural log is 1 over x, but I have x to the fourth, I can't use the derivative rule yet. However, there was a logarithm property. It was the power rule, I believe is what they call it for logarithms, that says if I have natural log of a value here, I can bring that exponent down to the front. Okay, I'm not going to prove the rule or show why it works in this video, but there is a rule that says we can do that. Well, now taking the derivative, remember a coefficient 4 we can just leave, and the derivative of ln x is 1 over x. So we usually write that as 4 over x, but 4 times 1 over x is not incorrect. All right, and that's it. That's the derivative of natural log of x to the fourth power. One key thing I do want to point out before we move forward is, let me go ahead and get a different color here. This is not the same as this, by the way. Okay, our original f of x is not ln x in parentheses to the fourth. That derivative would be different. This is a natural log of, like this, x to the fourth. Alrighty. This next example, natural log 4, and I apologize. I wrote that slightly incorrect because it should be 4 over x cubed. I think I was just writing in a hurry there. So otherwise it wouldn't work. It's 4 over x to the third. Okay. So this has division. This is natural log of this stuff, where the next example has multiplication, natural log of all of that stuff, not just natural log 4 and then times x. It's natural log of all of that. Often textbooks won't write parentheses because it's assumed. If they wanted the x out of it, they would have wrote x times ln 4. Okay, that is different. That's different than what is being presented. So without the parentheses, it's still understood it's natural log 4x. On that note, both of these are very similar. Natural log 4 times x, if we have multiply, that is equivalent to do a natural log 4 plus natural log x. Okay, it's the product rule for logarithms, and therefore if multiply is addition, the division here is subtraction. All right, now that we rewrote this function, derivative again is easy. We have derivative of ln4. ln4, you could put that in your calculator, it's just some number. Okay, the derivative of any constant is 0. So that derivative is 0. So f prime of x, I'll go ahead and write the 0 to show that we did in fact do that, but obviously you wouldn't write 0, whatever. Now, ln x to the third is just like we had above, right? So really I'm thinking of this piece as a negative 3 ln x. So the derivative of that is negative 3 times 1 over x. And therefore, the final derivative combining like terms is negative 3 over x. Right? There's that solution. Here's that solution. Likewise, we could do the third example here. Derivative of natural log 4, just like above, that's 0. And then derivative of ln x is 1 over x. And 0 plus 1 over x is just 1 over x. So if you go through the textbook, they give an additional formula for log base 5. Remember, natural log just means it's a base e, right? All these with ln, it really is just a log, but it's base e. It happens so frequently in not just math courses, but in business applications that they use its own special symbol, ln. Well, log base 5, there is a separate formula for this, but I am just going to say that it's based on the change of base formula. The change of base formula, how I teach it, is that we could do log any base, but again, we've been using ln, and I know the derivative of ln is 1 over x, so let's use that. It says we could take natural log of the bigger number here, x, divided by natural log 5, that base. All right, now if we do derivative, it looks quite ugly, and if you've seen quotient rule or later when we do quotient rule, you might be inclined to do it, but remember natural log 5 is a number. I could plug that in a calculator. So really this is like saying 3 over ln 5, all a number, times ln x. So the derivative then, since this is all constant, should have given myself a little more room, I'm sorry. 3 over ln 5 times 1 over x. And actually I can scroll just a little. And therefore 3 times 1 in the numerator, and then x ln 5 in the denominator. Usually we would write it like that, but even the form right above, it's not incorrect. Okay, it's just a matter of preference. That is how you evaluate derivatives of logarithms that are not base e. When it's not an ln, notice all that happened is we do the rule like we normally would, but we end with a divided by ln whatever that base was. Okay, so to recap, let's say if I want a derivative of log base 2x, the derivative then is just, it's still 1 over x, but we get ln 2 in the denominator. That will always occur. So if you're more inclined to formulas, that's the formula. It's 1 over x, and then ln whatever your base is. Okay, moving back up here. So we had said, or I had said at the beginning, derivative of e to the x is the easiest thing because it's just e to the x. If I have a constant stays, derivative of e to the x is e to the x. Then sum or difference, right? So I could then do derivative of negative 2x, that's just negative 2, and the derivative of 5 is 0. I don't really need to say plus 0, right? But the derivative of a constant is always 0. That's it. I'm leaving myself a little bit of room here because I want to explain something here in just a second. But let's look at this next example. Remember that e is still a number. It's an irrational number, but it's a number. It's like pi. E is approximately 2.72, I believe. So if I have x to some number, the rule is that you bring down the power and subtract 1, right? So as ugly as this next one is, if e is in the exponent and x is your base, the derivative is, I'm going to bring down that e, x stays the same, right? Like the derivative of x squared is 2x, the x stays the same. And the new exponent is e minus 1. This next part, since it's subtract, derivative is negative 2 e to the x. Doesn't change. This here doesn't come up often, but if you see it, that's what's going on. Okay, they're using power rule. All right, so the derivative of e to the x is e to the x. But if I have 4 to the x, I mean, is the derivative just 4 to the x? Not quite. It's missing one little thing. The easiest way to remember this is if I had a log base 5 back, I'm moving back over here, I ended up dividing by natural log of the base of 5. So if I have an e to the x, think of this as an inverse of the log, right? Then the rule says I have to multiply by natural log of 4. Whatever that base is, you leave it just like e to the x, but then you add, or you multiply, I should say. But in addition, you have multiply ln 4. So why is that? Well, if I have e to the x, and I multiplied by this base, ln e. So, well, I guess I left room here, but it would work better up here. If I multiplied by ln e, like I said here, the rule is to multiply by the base down the 4 to the x, ln e is just 1. So sure, you could say the rule is always any exponential, you multiply by natural log of that base, but you're wasting time with e because ln e is just 1. Okay, that's the reasoning behind that. So did we actually do that in this one? Yeah, but we don't write it because multiplying by 1 is not necessary. All right, last example. This equation of the tangent lines, it will continue to come up. Every section you work in calculus or business calculus, you will see equation of tan lines. An equation of any line, we need a point, y1 and x1, right? We need a point, and we need a slope. Remember, a fancy way of saying slope in calculus is derivative. So let's go back to f of x and let's find the derivative, because I need that for m. Derivative of 1 is 0. The derivative of ln x to the fourth is 4 over x, based on the rules above. Now, this tells us, though, it's at x equals e. So I actually do have x1, but I don't have my y1 yet. And I don't quite have my m because I need to still substitute e. Okay, f prime of e is just your m. Whatever x they give you, you substitute that into the derivative, that's your m. So we also have x1, but we need our y1 still. Well, that is simply the original function evaluated at e. And ln and e are inverses. These two cancel, they make 1. But since it's to the 4th power, we get 4. Another reason is, remember that we could bring that exponent down by the properties. If I have ln, something with an exponent, I could bring that 4 down. And now ln e is 1, so 1 plus 4 is 5. So we have everything now. Y minus 5 equals m, which is 4 over e, x minus x1, which is e. Okay, sometimes they're okay with you writing this form. Sometimes they want you to add the 5 and get it in slope-intercept, right? Y equals mx plus b. So I'm going to first leave it like that, but then we will distribute 4x over e, right? Distribute. And then this, the e's would cancel, so we just get minus 4. Add 5 to both sides. I'm going to write 4 over e x because now it looks like mx, right? mx plus b. And when I add 5, we get 1.